All right, welcome to Good Choices, which unfortunately in this case does seem to involve a lot of pain and suffering. This is not easy, but it's not meant to be easy. If we go to the LPIC site, so I'm actually already there here, so let's duplicate the tab, and let's go to Home, and then oh, I don't understand why the okay, this is good enough. It seems like these options up here. Oh, it's because we're at learning.lpic.org now instead of just lpic.org. Let's just go to lpic.org. Okay, and now we've got this certification tab here. So this is a professional cert, so it's not meant to be easy. If you want something easy, entry level, get into the field without knowing anything, Linux Essentials is the way to go. For me, I just think that would be kind of a not the best use of my time because I have that associate's degree. I have 8 years of experience. I am a professional, and I want to validate the fact that I'm a professional. So, pain for me. Alright, so last video, we went to, we did lesson 102.2, and then we're going to start lesson 102.3. You can see I do have this highlighted because I actually did make a video, tried to make a video, but so this was released the 28th. It is now the 7th, so I definitely need to do a better job being consistent with these. I haven't made a video for 1, 2, 3 days later, so I'm never going to remember anything if I'm this consistent. But at the same time, I need to be careful not to be too hard on myself and just find a solution for keeping going. So the last thing I'm going to say, and then I'm going to move on and spend time studying, is I actually can't really, like, for me, sleep is like one of the most important things. This is kind of off topic here, but I when I have caffeine, get anxious, get jittery. I think my BFRB problem gets worse, and caffeine is just something I try to avoid. Sometimes I'll have it as early in the morning as possible through like white tea. I was doing that for a while. That was actually really nice. But caffeine, after it is processed by the body, creates 3 chemicals, and 2 of them cause jitters, cause crashes, cause interference with sleep. One of them gives pretty much most of the benefits and doesn't have these drawbacks. So I'm just kind of plugging this energy drink, not to be a shill or anything, or kind of take this channel away from, you know, what its intentions are, which is to be a technology channel, not an energy drink channel. But I just want to say, if over the course of the few days these videos are more consistent and higher in quality, I just want to be open and transparent about why. It's because I'm high on paras on this chemical, which is just a component of caffeine. All right, so let's get right down to business. We're on 102.3 lesson 1. The topic is 102 Linux installation and package management, and the objective is to manage shared libraries. Introduction. In this lesson, we will be discussing shared libraries, also known as shared objects, pieces of compiled reusable code like functions or classes that are recurrently used by various programs. To start with, we will explain what shared libraries are and how to identify them and where they are found. Next, we will go into how to configure their storage locations. Finally, we will show how to search for shared libraries on which a particular program depends. All right, and I just need a quick 1 second break here. All right, just give me a second here. All right, I'm back. Audio levels look pretty good. On my Focusrite, they look good too. I don't have any yellow or red. So next section, concept of shared libraries. Similar to their physical counterparts, software libraries are collections of code that are intended to be used by many different programs, just as physical libraries keep books and other resources to be used by many different people. To build an executable file from a program's source code, two important steps are necessary. First, the compiler turns the source code into machine code that is stored in so-called object files. Secondly, the linker combines the object files and links them to libraries in order to generate the final executable file. This linking can be done statically or dynamically. Depending on which method we go for, we will be talking about static libraries, or in the case of dynamic linking, and we remember that dynamic linking is not defined. Oh, dynamic linking is just an alternative to static linking, which we will learn about later. So this linking can be done statically or dynamically, depending on which method we go for. We will be talking about static libraries, or in case of dynamic linking, about shared libraries. Let us explain their differences. Static libraries. A static library is merged with the program at link time. A copy of the library code is embedded into the program and becomes part of it. Thus, the program has no dependencies on the library at runtime because the program already contains the library's code. Having no dependencies can be seen as an advantage since you do not have to worry about making sure the used libraries are always available. On the downside, statically linked programs are heavier. Shared or dynamic libraries. In the case of shared libraries, the linker simply takes care that the program references libraries correctly. The linker does, however, not copy any library code into the program file. At runtime, though, the shared library must be able to satisfy the program's dependencies. This is an economical approach to managing system resources, as it helps reduce the size of program files and only one copy of the library is loaded into memory, even when it is used by multiple programs. All right, shared object file naming conventions. The name of a shared library, also known as SONAME, SONAME. SO probably standing for shared object. So SONAME, SO, shared object name, follows a pattern which is made up of three elements. The first element, library name, normally prefixed by lib, L-I-B. The second element, SO, which stands for shared object. The third element, version number of the library. Here is an example of a shared object file name. LIB, so there's the prepend of the library name. Now the library name is pthread, P-T-H-R-E-A-D. Then the next component, so that whole first component, I guess, is the library name. The library name is LIB P-T-H-R-E-A-D. That LIB prefix is a extra indicator to make it clear that it is a shared object file name and that the library name is pthread. The next section is SO, which stands for shared object. And then the final section is the version of the library, in this case, version 0. By contrast, static library names end in .a. For example, lib thread. Okay, this is a bad example. I'm going to ask the AI about this, but we can see in this example, this is actually a dynamic library because it's using a number here. If this were a static library, the way we could tell the difference is we would see a letter here. But I don't like this example because we can see it only uses 2 parts instead of 3. It uses the library name, and then it uses the version of the library, which we can see is specified using a letter, so we know it's a static library. But then we're missing this .so, and I don't know if that's a valid or if that's just an error. So I'm going to ask the AI. All right, and then my question will be, in the static library name example, libpthread.a, is this a typo in this text where the errata would be libpthread.so.a? So the answer is no. Surprising. It is not a typo. The example provided in the text, libthread.a, is correct for a static library. Static libraries commonly have the file extension .a to distinguish them from shared libraries. The .a extension, okay, but they're not talking about... The .a extension indicates that the file is an archive library containing object code that is linked directly to an executable at compile time. On the other hand, shared object files, also known as shared libraries, use the .so extension. Okay, so I guess static libraries aren't shared, so you don't need that .so. The .so stands for shared object, which I guess is a synonym for a dynamic library, and indicates that the file contains code that can be dynamically linked and loaded by multiple programs at runtime. So in summary, you don't need the .o when you're using a static library because a static library is not a shared object. It's dynamic, and it can't use let me see here. So it can't be dynamically linked and loaded by multiple programs at runtime. A static library does not have that feature, so it's just 2 parts .a to differentiate it from a dynamic library, but there's actually further differentiation .so. So I'm kind of surprised they need to use the .a. They can't just keep the letters. So let me ask this is what's so powerful about these AIs. I can actually ask that question. For me, it's typically been pretty frustrating to read through documentation stuff because I have so many new questions. Oftentimes before I read the documentation, I have some questions, but then after I read it, it's I have so many more questions, and the documentation just did not answer any of them. So that's the power of these AIs. Let's ask this a question. So since the inclusion of .so is a way to determine whether a library is static or dynamic, why is the further why is further differentiation why is further why is the and this is the version. Why is the version of the library letters for static libraries but numbers for dynamic, since you already know which is which due to the absence or presence of .so. Okay, so the answer to that question is I have raised a valid point. Thank you. The inclusion of the .so extension in the file name already distinguishes shared libraries, also known as dynamic libraries, from static libraries. The use of version numbers in the naming convention is primarily for shared libraries, not static libraries. Version numbers are commonly used in shared library naming conventions to indicate different versions of the same library. This allows programs to specify the specific version of a shared library they require. Yep, we know that. Ensuring compatibility and avoiding conflicts when multiple versions of a library coexist on a system. The version number is typically represented as a series of digits separated by dots, such as for this dynamic library. And we know that for two reasons. The first reason we know that is the .so portion of the library name is included, and it's using numbers instead of letters. So there's two examples of that there. Static libraries, on the other hand, are typically used at compile time and are directly linked to the executable. They do not have the concept of versioning in their naming convention because their code is directly incorporated into the resulting binary. The absence of the .so extension already distinguishes static libraries from shared libraries. While the use of version numbers is not necessary for static libraries, it is a common convention for shared libraries to facilitate version management and compatibility control. Okay, I guess that could be that's the answer right there. For a static library, it's static. It's not dynamic. So there's one version of a static library, version A. So just so you don't get confused that there's going to be multiple versions of this static library, we have a scheme that makes it more clear that this is the only version of it because it's static. Note, because the files containing shared libraries must be available when the program is executed, most Linux systems contain shared libraries. Since static libraries are only required in a dedicated file when a program is linked, they might not be present on an end user system. GLIBC, GNU C library, is a good example of a shared library, so we'll have the .so in there for shared object. On a Debian GNU/Linux 9.9 system, its file is named libc.so.6. Such rather general file names are normally symbolic links that point to the actual file containing a library whose name contains the exact version number. In the case of glibc, which is the GNU C library. This symbolic link looks like this. All right, and let's see if the symbolic link looks the same on my home lab. It's probably a different version number, so let's identify the differences in version. So the command is ls-l/x86_64. That's the command listed in the example. It might not be the exact same command on my system, but we'll try this one first. /libc/so/6. And this is where there's probably going to be a difference. I doubt I'm using .6. Okay, so yeah, it turns out I am doing .6. Let's try it without that file there. See, okay, so I do have other options on there. I have .7. I have just all kinds of different options. Actually, these options are for different things. So let's do a pipe grep and do libc. And let's do libc dot. We'll escape the dot because it's a regular expression. So we're looking for not just any character, we're looking for the dot character. And I forget how to escape here. I thought that's how, but apparently that's not how. But we can do, we know it's a shared library, so we can do .so. There we go. And now we've got, so it actually looks like there's only version 6. So it does match that. Now it is a symbolic link, just like we see. The symbolic link in the example goes to libc-2.24, the exact version. The exact version in my home lab is 2.7. So my home lab is a little more recent than this documentation. Kind of concerning because I don't want to be studying something out of date, and my home lab is already very much out of date by intention. But, why just include a new example that shows, and why update this, every week? So I think this is fair. Good example. And we saw, this exists in my home lab just as is written here. This pattern of referencing shared library files named by a specific version by more general file names is common practice. Other examples of shared libraries include libreadline, which allows users to edit command lines as they are typed in and includes support for both Emacs and Vi editing modes. libcrypt, which contains functions related to encryption, hashing, and encoding. libcurl, which is a multi-protocol file transfer library. Common locations for shared libraries in a Linux system are /lib, /lib32, /lib64, /user/lib, /user/local/lib. Note, the concept of shared libraries is not exclusive to Linux. In Windows, for example, they are called DLL, which stands for Dynamic Linked Libraries. Okay, so that's really good to know. What we're learning about here is the equivalent of DLLs in Linux. In Windows. In Linux, these are called shared libraries. We also have static libraries, of which the similar library in Linux I'm not so sure about. I'm pretty sure it's not a dynamic link library because we know that static and dynamic libraries are different things. But I think the shared objects, the dynamic libraries, those are the really key ones that are where most of the 80-20 rule or well, those are the ones to know. So let's do ls-l slash lib. There we go. I've got all kinds of what do we got here? We got shared libraries. Yeah, we've got a few shared libraries in there. Let's do a pipe grep for .so. Okay, so we've got yep, we've got some shared libraries. So we've got two really clear ones, libhandle. We've also got like a pretty unclear one, ld-linux, that doesn't start with lib, so that's kind of an interesting one. And then we've got another one that has the .so syntax, but it doesn't have a version number after it. It's just got that, and it starts with klibc. So those are some interesting files that don't probably beyond the scope of this lesson, but might be relevant later on. Let's take a look at if there's a .a file, because that's a static. Don't have it. All right, so go back to .so. Let's look at lib32. Okay, lib32 has more the meat and potatoes in it. There's all kinds of lib prefixed names with that syntax that we learned about in this lesson. lib64 coming up short on that. Don't even have any lib prefixed ones. We don't have any static ones. So lib32 is where it's at. Don't see any static in lib32. All right, so let's take a look at user lib. Yep, quite a few things going on in there as well. Not nearly as much as lib32. Let's take user local lib. Nothing. So lib32 on my system is the common location for shared libraries that contains the most shared libraries on my system. All right, next section, configuration of shared library paths. I need a break here, but I'll be right back. All right, welcome back. No time to waste. I closed my update energy drink tab. I'm going to pull that up again because, again, I'm feeling some kind of light switch go on in my brain. And, yeah, so configuration of shared library paths. The references contained in dynamically linked programs are resolved by the dynamic linker, sd.so, which apparently itself is a dynamically linked program. And it can also be called ld-linux.so when the program is run. The dynamic linker searches for libraries in a number of directories. These directories are specified by the library path. The library path is configured in the /etc directory, namely in the file /etc/ld.so.conf, and more common nowadays, in files residing in the /etc/ld.so.conf.d directory. Normally, the former includes just a single include line for star.conf files in the latter. So here's the this is the library path. Let's take a look at it on my home lab. cat /etc/ld.so.conf, and that is a file that has the library path that uses this include command, and then the path is /etc/ld.so.conf.d, slash star conf. So files residing in this directory, conf.d. So we've got a file here in slash etc lt.so.conf, and we've also got a directory in etc lt.so.conf.d. D probably stands for directory. But the files residing in the so the library path is configured in the etc directory, namely in this file that we took a look at, and more common nowadays in files residing in that directory. Normally the former includes just a single include line. For the star.conf files in the latter, which we saw that is what mine includes, the slash etc slash ld.so.conf.d directory contains star.conf files. So here we can see, looks like there's only one file here. Let's take a look at how that's different in my home lab. Okay, so we've got a number of extra files here. We've got 5 conf files where only one was listed. Actually, 2 were listed. But we've got the same one, libc.conf, that they've got. We've got the same one, x86_64 dash linux.gnu.conf that they've got. But we've got 3 extra files, including one with a kind of funny name, fake root. I'm going to ask ChatGPT, and then I'm going to say, hopefully if I don't lose that. Okay, so these are the files that showed up at my home lab. These are the files that show up on my home lab. Okay, and I'm going to say, why do I have extra files? All right, and then the answer: the presence of additional files in your slash etc slash ld.so.conf.d directory could be due to various factors, such as the specific configuration of your system or the software installed on it. Here are some possible reasons for the extra files. Package installations. Certain software packages may add their own configuration files to the slash etc slash ld.so.conf.d directory during installation. These files are used to set specific paths for shared libraries required by the respective packages. Architecture-specific configurations. The files prefixed with x_64, which we do see in the example there, but the extra one I have, I368, suggests that your system may have both 64-bit and 32-bit libraries installed. The files in question are likely to contain paths for the respective library directories. And remember, I am this Ubuntu shell, the bash shell I'm accessing for the Ubuntu installation, is a virtual machine. Compatibility configurations. Files like zz underscore, which I believe I do have on there. Yes, I do. Or fake root, that's the interesting one, may be related to compatibility or special handling requirements for specific software or configurations on your system. It's worth noting that the exact reasons for these files can vary depending on your specific system setup, installed software, or any customizations you may have made. To determine the specific purpose for each file, it's recommended to examine their contents or consult the documentation of the packages or software installed on your system. Alright, these *conf files must include the absolute paths to the shared library directories. So they're not going to start with a... Oh, no, a relative path wouldn't start with a slash. These are absolute paths, so they're going to start with a slash. Alright, and here we can see we've got 2 absolute paths that start with a slash. Let's see what my home lab looks like. cat/etc.so.conf.d/x86_64 -linux-gnu.conf. And we've got an extra one here. So the extra, and it does say multi-arc support, probably multi-architecture support is what that stands for. We've got an extra /user, and that extra one is in user/local/lib, but after that it's the same file name. The ld-config command takes care of reading these config files, creating the aforementioned set of symbolic links that can help to locate the individual libraries, and finally of updating the cache file /etc/ld.so.cache. Thus, ld-config must be run every time configuration files are added or updated. Useful options for ld-config are -v and -ch verbose. Display the library version numbers, the name of each directory, and the links that are created. So let's take a look at how that's different on my home lab. Sudo ld-config -v. And it's a sudo, so I need my root password. There we go. I've got a lot more output, but we can see with these ellipses in the example, they are abbreviating their output. Let's see if I've got a libnes_my_hostname at the top. I do not. So I'm going to run that again with a grep. Okay. Yeah, I don't see that. So mine looks quite a bit different from theirs. So I have different config files, which probably makes sense because I have a different machine. So we can see, for example, how libfuse.so.2 is linked to the actual shared object file libfuse.so.2.9.7. Alright, -p or --print-cache prints the lists of directories and candidate libraries stored in the current cache. Let's take a look at that on my home lab. Sudo ld-config -p. There we go. So we should have some directories and candidate libraries. So we do, and we've got the symbolic links. Alright, looks good. Note how the cache uses the fully qualified shared object SO name of the links. Sorry, I've been sitting in one position for too long, so I'm changing my position here. And we can see the fully qualified shared object name includes the x86_64. Alright, I've got a better posture here. So let's take a look at that one on my home lab. Sudo ld config -p pipe grep libfuse. There we go. We got the same version. .2, same architecture. Everything is the same. If we long list /x86 _64 -linux -gnu /libfuse.so.2, we will find the reference to the actual shared object file libfuse.so.2.9.7, which is stored in the same directory. So ls-l /lib /x86 _64 -linux -gnu /libfuse.so.2. So that's what happens when we long list. We do that with the -l, and we find the reference to the actual shared object file .2.9.7 in the same directory. Let's see if I've got .2.9.7 on mine. ls-l /lib /x86 _64 -linux -gnu /libfuse.so.2. So yep, I've got 297 as well. Note, since it requires write access to /etc/ld.so.cache owned by root, you must either be root or use sudo to invoke ld config. For more information about ld config switches, refer to its manual page. Okay, so we're going to do that quick. We're going to do man ld config. We should see all the switches there. We've got -c, -uppercase -f. Yep, so that's how you look at the manual page. You just do man space, and you get the manual page. In addition to the configuration files described above, the ld_library_path environment variable can be used to add new paths for shared libraries temporarily. It is made up of a :separated set of directories where libraries are looked up. To add, for example, /user/local/mylib to the library path in the current shell, you could type this. I'm not going to type that because that defines a variable. I will see if that's already defined. So I'm going to do the echo command, echo *ld_library_path to check its value. All right, so yep, it's not defined there. To add /user/local/mylib to the library path in the current shell session and have it exported to all child processes spawned from that shell, you would type the export command. So if you don't type the export command, all you do is add let me see. You add an environment variable to the path in the current shell session. But if you use the export command, then you add the library path in the current shell session, and then it is exported to all child processes spawned from that shell. So let's say you have let's say you run something on your system that as a result runs something that takes in system variables. If all you do is define the system variable in your shell and don't use the export command, that thing that ran as a result of what you ran would not know your variable that you defined before you ran it, because that's a child process that's kicked off by what you ran. And in order for child processes to know about defined variables in a shell, you have to use the export command so that they are passed to that child process. To remove the ld underscore library underscore path environment variable, just type unset, which is a very confusing command because you don't need to type set. You just don't need to type any kind of command. So I would think it was remove or delete or something like that, but it is unset. To make the changes permanent, you can write the line export so that it can be used by child processes in one of the bash's initialization scripts, such as /etc/bash.bashrc or tilde/.bashrc. Note, ld underscore library underscore path is to shared libraries what path is to executables. For more information about environment variables and shell configuration, refer to the respective lessons. All right, so we're almost done. We just got this one section of reading and then the exercises. So I'm going to make it my goal to finish this this morning, today, before I move on to something else. But I'm kind of running out of steam a little bit, so I'm going to take some time to recoup. So I'll be back in a few minutes. All right, I'm back. Let's close out this video in this section. So the last part of the reading is searching for the dependencies of a particular executable. To look up the shared libraries required by a specific program, use the LDD command followed by the absolute path, so a path that starts with a slash, to the program. The output shows the path of the shared library file as well as the hexadecimal memory address at which it is located. Okay, there we go. Let's take a look at my home lab. So LDD/USR/bin/GIT. And there we go. Looks like even, nope, this is a different address, okay. Likewise, we use LDD to search for the dependencies of a shared object. All right, let's see what that looks like in the lab. LDD/lib/x86-linux-gnu/libc.so.6. There we go. We got different addresses for it, but we've got the same two files popping up. With the -u or -- unused option, LDD prints the unused direct dependencies if they exist. LDD-u/USR/bin/GIT. Okay, so I don't have any unused direct dependencies. The reason for unused dependencies is related to the options used by the linker when building the binary. Although the program does not need an unused library, it was still linked and labeled as needed in the information about the object file. You can investigate this using commands such as readelf or objdump, which you will soon use in the explorational exercise. Alright, so here's the guided exercise. First exercise, divide the following shared names into their parts. So let's use Microsoft Paint, the greatest application ever developed in the history of the world. Way better than Linux, way better than Grub, any of this stuff. Microsoft Paint is the best thing ever made by computers. AIs in the next 10, 100 years, Like, yeah, they might have some impact on society, but Microsoft Paint will really be forever in the halls of the most prestigious academic institutions, and certainly on this channel. I can't I can't emphasize enough how much I love Microsoft Paint. All right, so the complete file name, the library name, is going to be linux.vdso. The SO suffix is just SO for each of them. And then the version number is .1. So I think this is what they're looking for. Really, really easy. I'll just write it all out. Now here's where it gets a little tricky, because is the library name ProCPS or is it libprocps? I think it's libprocps, but we'll see the difference there in the the answer. So I'm just gonna type all this out. It's pretty obvious and self-explanatory, but I can do it out of order, so I can just do the SO for each of these to save some time. All right, and then I can do the numbers. So 2, 6, 0, 2. No trick questions here, just really easy to understand. Kind of beating a dead horse. It's just so obvious, the naming scheme, which is good. It's a good naming scheme when that's the case. x86, 64. Oh, not this. Nope. See, I almost got it wrong too. So I guess this is a good exercise. All right, let's see how that compares with the answer. All right, so yep, that column looks right. Now here's the key. Yep, okay, so the lib prefix is included in the library name. The full library name includes that lib prefix. Didn't mistype anything. Let's take a look at the version numbers. Yep, 162.602. There we go. All right, that's a freebie. Hopefully the test has questions like that. All right, second guided exercise. You have developed a piece of software and you want to add a new shared library to your system /opt/lib/mylib. You write its absolute path in a file called lib.conf. In what directory should you put this file? Interesting question. I don't know. I'll have to go back to the reading. I think that's fair game. Not the answer, but figuring out from the reading. So this is my lib.conf. I'm pretty sure you want to put it in that star.conf file. So my answer is /etc/ld.so.conf. That's the answer there. Okay, so let's see if I got that one right. Yep, /etc/ld.so. Oh, no, I got it wrong. So I thought I didn't even read the question right. So in what directory should you put this file? So I read it as, in what file should you put a command pertaining to the config file? So completely got this one wrong. The directory is etc/ld.so.conf.d. So if we go back to the reading, about star.conf. We can see if I read the question correct, I would have gotten it right, because directories are, because the references contained in dynamically linked programs are resolved by the dynamic linker, ld.so typically, or it could be called ld-linux.so. When the program is run, the dynamic linker searches for libraries in a number of directories. These directories are specified by the library path. The library path is configured in the /etc directory, namely in the file /etc/ld.so.conf. So that's where the dynamic linker searches for libraries. No, wrong. That's the library path. The library path is in that file. But that's just an old school way of doing it. More commonly nowadays, the files residing in the /etc/ld.so.conf.d directory are the files used by the dynamic linker. And I'm gonna ask that to the AI, because I'm really confused about this. I'm gonna say, are the files in the /etc/ld.so.conf.d directory used by the dynamic linker? Yes. So, yep, I think I have a good understanding of that. The files in the /etc/ld.so.conf.d directory are indeed used by the dynamic linker. The files are collectively contribute to the configuration of the library path used by the dynamic linker when resolving references to external libraries. So next question, what is a dynamic linker and where is it on a Linux system? And I'll keep reading the answer to the prior question. Each file in the /etc/ld.so.conf.d directory typically represents a separate configuration snippet that specifies additional directories to be searched for binaries. These files can have any name as long as they end with the .conf extension. The dynamic linker reads the contents of these files and incorporates the specified directories into the library path search process. By using separate files in /etc/ld.so.conf.d directory, it becomes more flexible and modular to manage the library path configuration. Instead of modifying a single potentially large configuration file, administrators can add, remove, or modify individual files in the /etc/ld.so.conf.d file as needed. This approach allows for easier maintenance and organization of the library path configuration. So it's kind of like using Jinja files in Python in that regard. To summarize, the files in the directory mentioned are indeed utilized by the dynamic linker as part of the library path configuration process. A dynamic linker, also known as a runtime linker, is a program responsible for resolving and linking references to external libraries at runtime for dynamically linked programs. It is an essential component of the execution process in a Linux system. On a Linux system, the dynamic linker is typically named ld.so or ld-linux.so. Perfect. It is located in a specific system directory known as the dynamic linker search path. The search path includes directories such as /lib and /user/lib, where the dynamic linker itself is usually located. The exact location of the dynamic linker can vary depending on the specific Linux distribution and system configuration. However, it is typically stored in a directory within the search path to ensure that it can be found and executed when needed by dynamically linked programs. The dynamic linker is invoked automatically when a dynamically linked program is executed. It resolves and links the references to external libraries specified by the program, allowing the program to access the required functions and symbols from those libraries during runtime. In summary, the dynamic linker is a program on a Linux system responsible for resolving and linking references to external libraries at runtime. It is typically named ld.so or ld-linux.so and is located in a directory within the dynamic linker search path. Perfect. All right, so to the exercise, the question is, what directory should you put this file? So it's /etc / and then it was like ld.so.conf.d, I think. Yeah, ld.so.conf.d, perfect, in the etc. And then what command should you run to make the changes fully effective? Let's look that up in the reading, not in the answer key. I think it's ld-config. Oh, so I saw the answer key there. So the answer is ld-config. Let's try to figure out where that was mentioned. Here we go. So, okay, the file, the ld-config command takes care of reading these config files, creating the aforementioned set of symbolic links that help locate the individual libraries, and finally of updating the cache file. Thus, ld-config must be run every time configuration files are added or updated. So let's take a look at the answer key. So the answer key indeed says you use ld-config to make the changes fully effective. All right, last question of the guided exercise. What command would you use to list the shared libraries required by kill? Oh, and this is a tough one. Let me go on my Linux box. We'll take a look at the history. So the shared libraries, okay, required by that kill. That is an interesting question. So shared libraries. So I'm thinking you would use a ld config command. Then you can use -p maybe. So would it be ld config -p kil? Okay, maybe not that. So let's look for list the shared libraries and see if we can find that in the reading before looking. Before looking at the answer, let's see if we can find it in the. Yeah, so -p prints the list of. Oh, in the cache. We're not looking at it for the cache. We're looking for all of the required shared libraries. Huh. Oh, you know what? Maybe this is it. Yeah, okay. So my answer is LDD, and then we can use the which command, I believe. So which kill. So there it is, and now we can do LED bin kill. There we go, and here's all the shared libraries. Perfect. Okay, so let's take a look at the answer. Highlight the full question. Oh, this is interesting. There's no answer given for this one. Oh, no, here it is. Yep, LDD /bin /kill. And if you don't know where it is, you can do this which command to figure out. Perfect. So next is the explorational exercises. I'm going to take another short break. I'll be right back. All right, I'm back and feeling better than ever. Let's close this thing out. Explorational exercises. Number 1. OBJDUMP object dump is a command in command line utility that displays information from object files. Check if it is installed in your system, which OBJDUMP. If it is not, please install it. Alright, so here's my beefy system, which OBJDUMP, and it's installed. I'm in luck. Okay, so use OBJDUMP with the -p or -- private headers option, and grep to print the dependencies of glbic. All right, that's an easy one. So jdump -p pipe. Let's just do it without a pipe for now. Oh, so we've got a problem here. Okay, so we'll do a man on OBJDUMP. So display system information. So for -p, that's for private headers. So let's take a look at the example for that. Element NOP. There we go. So that's so here it is. Print information that's specific to the object file format. The exact information printed depends upon the object file format. For some object file formats, no additional information is printed. All right, let's try it without an option. OBJDUMP. So that just gives the. Okay, so we do need a file, I think. So what do? We do now we need grep. So glbc. Let me try this. So which glibc command not found. Okay. Alright, I need to switch chairs quick. I'll do that without pausing. All right, my chair is now switched to a better chair. One thing I probably should do a video on at some point is just how important when you're using a computer, you know, ergonomics might seem like it's this thing where, like, you know, it's just more trouble than it's worth, and like if you're not comfortable and you can't spend, you know, a few hours at the computer because you're using this ergonomic equipment that just makes you not feel good. It's like, well, okay, we'll keep up with that bad posture and see what happens. For me, my upper back, just after, you know, months, and again, you know, it would feel better. It would feel like it was the way to go because it would feel fine. But after months, I would get this severe upper back pain. And I just changed up my whole posture, and I started using a saddle chair. I guess that was the main thing. No more back pain. It just magically goes away. You know, it's worth that little bit of adjustment at the beginning where it's like, this doesn't feel super comfortable. It's like, well, just stick with it for a while. And everything should. The reason it doesn't feel comfortable is you're used to being in this position that is causing you long-term pain, or leading to it. The muscles that are required to maintain good posture are weak and underdeveloped. All right, so we're trying to get this command to work here. I don't know how to enter this command. Like that? Nope, so there's no such file. So I think I need to feed it like an output file. So let me do results.txt pipe grep glibc. No, there's no such file. So I guess I'm going to go down to the answer because I don't know how to run this command. You know what? Before we go to the answer, let's see if obj-dump was in the reading. I think going to the reading makes much more sense than going right to the answer. Okay, so you can investigate this using commands such as read elf or obj-dump, which you will use in the explorational exercise. Okay, so the explorational exercise, I guess I'm not necessarily meant to know this before I do the exercise. Just based on what I read above, this is a guided exercise part of the training. So let's go down to the answer. Okay, so okay. So we need to feed it in the. Now, is this a linker? I'm not even sure what this is. Let me take a look at what this is from the reading. So it's a shared. This is glibc. This is just what glibc is named. The GNU C library is named libc.so.6, assuming you're using version 6. Okay, so I did not know that. I don't know how I was expected to know that. So to print out the dependencies, we would use the needed key term. To print out the shared object name, we would print out the shared object name key term. And to print out the dependencies, we would print out to move on to another object file. We would use to check the dependencies of bash, we need to feed it a different object file. So yep, I'm just going to enter all of these in, and then that should be the end of this video. '86, 64, All right, so there we go. There's our needed um, dependency. Okay, now let's take a look at the shared object name of this shared library, which is the GNU C. It's the GNU C library, shared library for the C programming language. So obj dump-p /lib /x86 _ 64 -linux -gnu /libc.so.6 pipe grep so-name. So there we go. There's the shared object name of it. Makes sense to me. All right, so now let's do the same for bash, but let's just look at the dependencies. And you know what? I'll do an extra. I'll go above and beyond. That's usually a good idea if you got the time for it. So I'm going to do obj dump-p /bin/bash, because that's where our bash is located. Let's do a which on bash just to make sure it's in the same place on my home lab as it is in the example here. All right, perfect, it is. So then obj dump-p /bin/bash pipe grep and eeded all in uppercase. There we go. And bash actually has quite a few dependencies. It looks like it needs that C shared library, so use the C programming language for quite a bit, but then it's got additional dependencies beyond that. And let's go above and beyond and take a look at the shared object name for bash. All right, so there is no shared object name for bash, which is maybe it's because bash is a static library. Let's ask the. I'm kind of interested in that, so let's ask the AI. Okay, so now I gotta finish this. It's kind of annoying how I have to finish for it to do it. But here's the question: is bash a static library? So the answer is no. Bash is not a static library. Bash, okay. So it's a shared. Oh, okay. Well, this is interesting. Bash isn't. So a static library is compiled object code that is linked directly to an executable at compile time. It becomes part of the final binary and does not require any external dependencies during runtime. On the other hand, bash is an interactive shell that interprets and executes commands entered by the user. It relies on shared libraries, dynamic libraries, to provide various functionalities, but it itself is not a shared library. It is an executable program that depends on shared libraries. The shared libraries that we printed out here: libtinfo, libdl, and libc. So, of course, obviously, it does not have a shared object name because it is not a shared object or a shared library, also known as a shared library. It is a executable that depends on shared libraries, but itself is not a shared library. All right, so that was a good lesson. I feel like I learned quite a bit. Again, if I seem like this is a higher quality video, which it likely is because just by nature of it being a bit longer than some of my other ones, I might see if I could get like a referral link on this or something, because I think this has been pretty darn good for me. So I'll include this in the link, and stay tuned for the next lesson, which will be 102.4. Thanks for watching.